Hello everyone, I am Dr. C. Prasanna Devi, Assistant Professor from the Department of Mathematics, Fatima College. Now, we are going to discuss about countable and uncountable sets. Before that, we have to know what is meant by a finite set. If we count the number of elements in a set A, then we can say that the set is a finite set. In mathematical, we convert this into a definition. That is, if there is a bijection between the set 1, 2 up to n to the set A, then we can say that the set is a finite set. A set which is not a finite set is called as infinite set. Next, we have to know what is meant by countably infinite set. A set A is said to be countably infinite set if there is a bijection between the natural numbers and the set A. Now, here are some examples for countable sets. All the natural number systems are countable, rational number system is countable, set of all polynomials of degree less than or equal to n whose coefficients or integers are countable. Now, a set which is not countable is called as uncountable sets. Here are some examples for uncountable sets. The set of all irrational number system and real number system and complex number system are all uncountable sets. At the same time, every interval is uncountable. Any interval in or which more than one point is uncountable. Set of all straight lines passing through the origin is uncountable. Set of all transcendental number is uncountable. Next, we have to know the cardinality of a set. In general, cardinality means number of elements of a set. Here are some results related to cardinality of a set. The cardinality of a countably infinite set is denoted by Aleph naught. The cardinality of an uncountably infinite set is denoted by C, continuum. And the results are n naught. Aleph naught is always less than C. 2 power Aleph naught is always equal to C. Aleph naught into C is always equal to C. Aleph naught power Aleph naught is always equal to C. Here are some results related to countable sets. As we know, subset of a countable set is always countable. Countable union of a countable set is countable. Finite Cartesian product of countable set is countable. Next, we are going to move on to the problems. So, this is the problem in December 2012 CSER question. According to the question, they have defined a set AJ which is a finite set and that contains exactly two distinct elements. Then we have to pick the correct options. These are all the options. Now we are going to look into each of options individually. This is the first one. Here AJ is countable and we know that countable union of a countable set is countable. Therefore, the set given in option 1 is a countable set. Therefore, option 1 is correct. Next, we are going to move on to option 2. According to this, we have AJ is countable and we have the result that Cartesian product of a countable set is countable. That means finite Cartesian product. Therefore, it will become a countable set and again the result countable union of a countable set is countable. Therefore, the set described in option 2 is a countable set. But according to the problem, they have mentioned that as an uncountable set. Therefore, option 2 is wrong. Next, we are going to concentrate on option 3. Here AJ is countable but it is an infinite Cartesian product, therefore it will become uncountable. Therefore option 3 is correct. Next is option 4. Here AJ is countable and we have the result that countable union of a countable set is countable. Therefore the set given in option 4 must be a countable set, but according to the problem they have mentioned that as an uncountable set. Therefore, option 4 is wrong. Next, we are going to move on to the next problem. This is a problem in December 2013. Which of the following subsets of R2 are uncountable? In option 1, they have mentioned a set that should satisfy the condition that AB must belongs to R2 and A is less than or equal to B. And option 2 is A plus B must be a rational number. For option 3, The elements in this set must satisfy the condition that AB belongs to an integer. And for option 4, they have mentioned that A and B belongs to Q. Now we are going to consider each options. So for the first option, we have to consider all AB in R2. And that satisfies the condition A is less than or equal to B. Here we have considered an irrational number. Suppose we consider root 2 and root 3. They satisfies the condition that root 2 is less than or equal to root 3. Therefore, irrational number system satisfies the condition given in the set 1. We know that set of all irrational number is uncountable. Therefore, the set given in option 1 is uncountable. Next, we are going to move on to the set given in option 2. According to this, again I am going to consider two irrational numbers. One is root 2, another one is minus root 2. So, when we add these two irrational numbers, we get 0, which is a rational number. Therefore, irrational number system satisfies the condition given in the set 2. We know that every irrational number system is uncountable. Therefore, option set given in option 2 is uncountable. Next is we have to consider a set that contains an element that should satisfy the condition AB belongs to Z. Again, we are going to consider two irrational numbers. One is plus root 2, another one is minus root 2. So, multiplication of this has become minus 2, which is an integer. We know that this irrational number system satisfies this condition, and we know that irrational number system are uncountable. Therefore, the set given in option 3 is uncountable. Next, we are going to move on to option 4. That is, according to option 4, we have to collect all the elements AB in R2 that should satisfy the condition A, B belongs to Q. This set is nothing but exactly the set Q cross Q. We all know that every rational number system is countable and finite Cartesian product of a countable set is countable. Therefore, the set given in option 4 is a countable set. Thank you.